In this video, we will talk about the acceleration in one dimension. Acceleration is a vector quantity, therefore it requires the specification of both direction and magnitude. In this video, we deal with one-dimensional motion, thus we can indicate vector direction by using positive and negative signs. Acceleration is the rate of change in velocity. Therefore, average acceleration is the change in velocity delta Vx over the corresponding duration delta t. The subscripts I and f correspond respectively to the initial and final positions. Note that in this case, the magnitude A bar of the average acceleration is equal to its absolute value. Also note that the magnitude is a scalar quantity. Therefore, it has a numerical value and no direction. In the International System of Units, Vx is expressed in meters per second, t in seconds, and the value of the average acceleration in meters per second squared. We often need to know the instantaneous acceleration, which is the acceleration of a particle at some specific instant, rather than the average acceleration over a time interval. But since we cannot freeze time and talk about motion at a specific instant, we compute the instantaneous acceleration as the average acceleration around that instant. This can be done by taking a very small time interval with respect to the total duration of the motion. Therefore, in one dimension and along the x-axis, the instantaneous acceleration is given by this formula, which means that it is equal to the limiting value of the average acceleration as the duration approaches zero. Thus, it is equal to the ratio delta Vx over delta t as delta t approaches zero. Note that the magnitude A of the instantaneous acceleration Ax is equal to its absolute value. If the velocities of the particle are known at different instants, this formula can be replaced with an acceptable precision by this other formula, which gives the instantaneous acceleration at a certain instant tn by computing the average acceleration between the previous instant tn minus 1 and the next instant tn plus 1. Also note that in this case, the magnitude an of the instantaneous acceleration axn is equal to its absolute value. In the International System of Units, Ax and A are expressed in meters per second squared. Example, a motorcycle moves along the x-axis. The instantaneous velocities of its center of mass are represented in the table below for equal time intervals, tau equals 1 second. 1. Calculate the magnitude A bar of its average acceleration between P0 and P5. 2. Calculate the magnitude A3 of its instantaneous acceleration at P3. Note that instantaneous is written between parentheses because whenever we say acceleration without specifying, we are talking about instantaneous acceleration. For question 1, we know that the magnitude A bar of the average acceleration is equal to its absolute value. We write its general formula and we apply it between P0 and P5 with the respective velocities Vx0 and Vx5, knowing that the duration delta t between these 2 points is equal to 5 time intervals tau. We replace Vx0 and Vx5 by their values. We replace tau by its value, and we get 4.2 meters per second squared. For question 2, we know that the magnitude of the instantaneous acceleration is equal to its absolute value. We write its general formula, and we apply it at P3, which means between P2 and P4 with the respective velocities Vx2 and Vx4, knowing that the duration delta t between these 2 points is equal to 2 time intervals tau. We replace Vx2 and Vx4 by their values. We replace tau by its value, and we get 4.5 meters per second squared. And this is all for this video. Thank you for watching.